We continue our week 1 lecture for engineering mathematics and modelings on vectors with the dot product, the definition, and some properties. Now if we go back to an example from physics and we have some kind of object and we apply a certain force over a certain displacement s. In this case we know that the work done by this force is equal to F times s. But this is only for a very simple case. What if we have a different situation where we have a box and we displace it, but the force for some reason is in this direction? The displacement might be the same, but we can see that there is no work done by the component of the force in this direction. So we can dissect F into an x direction and a y direction, and we see that because the y portion of F doesn't displace, there is no work being done by that component and only by the component in x direction. So this formula doesn't work for situations where the force and the displacement are not parallel. Now this is where the dot product can help. We are looking for, if I draw, let's say a force F, and we have an angle theta, and the direction of the displacement is in this direction. We're not looking for F times S, no, we're looking for the component Fx. Well, I'll just call it F. What shall I call it? Well, the projection of F onto this direction. This is the component of F that we want to multiply S with. But how do we get this component? Well, we know that that this is a triangle with a right angle, and we know that to get this part here, this component is the magnitude of F, because F is a vector here, the magnitude of F times the cosine of theta. This is the component in the direction of S of our original vector F. Now if you want to then determine the work done, hang on, S here is also a vector. So we can't just multiply it by S, we have to multiply it by the magnitude of S. And if we have a vector S and we have a vector F, and we have the magnitude of F and times the magnitude of S times cosine of theta, that is the definition of the dot product, and the dot product we will denote by a big dot. So the definition of the dot product between vectors F and vectors S is the magnitude of F times the magnitude of S times the cosine of the angle between these two vectors. And it doesn't matter if it's in 2D space, it doesn't matter if it's in 3D space, there is only one single angle between these two vectors. Now, there are different ways of calculating this. This is one definition, but if I have a vector A, which is equal to AX, AY, AZ, and I have a vector B, which is equal to BX, BY, BZ, then the dot product of A and B, which would be hard to calculate because I don't know what the angle is. We can calculate that, but we don't have to. This is equal to AX times BX plus AY times BY plus AZ times BZ. And so if we have our vectors in this form, we can calculate the dot product very easily. So for example, if we have the vector 1, 2, 3, dot product with minus 1, 0, 1. Well, let's make this 2. Then the dot product between these two is the first element multiplied with the other element. So 1 times minus 1 plus 2 times 0 plus 3 times 2 equals minus 1 plus 0 plus 6 is equal to 5. And this is also very important. The dot product between two vectors yields a single value, yields a scalar. This is also why it is sometimes called the scalar product. It's known as the dot product, the scalar product, and the inner product, just probably to confuse people studying math. So we can calculate this. Hang on. First write A dot B yields a scalar. And this is very important. Now, the dot product has some properties. And would it matter if I reverse the order of these two vectors? So if we have A dot B, is this the same as B dot A? And this property is called, well, if this is the case, we call the dot product commutative. Well, can we see this? Well, if we switch these two around, then we switch these around, switch these around, and switch these around, but we know that multiplication, the order of multiplication doesn't matter. So the dot product is indeed commutative. Is this the same? Is this the case for all mathematical operations? Absolutely not. In the next lecture series, in the next week, we will see the cross product, which is not commutative. Does it have other properties? Yes. If we multiply this, if we have A and we have the dot product of, let's say, B plus C. So if we were multiplying numbers, we would say, oh, there's A times B plus A times C. Well, this has a similar property. This is A dot B plus A dot C, and we call this property distributive. So it you can, when you have parentheses like this, you can distribute it this way. Do we have another property? If we multiply A dot B with a constant, we can move this constant through the parentheses. So this is the same as saying K times A dot B, or A dot K times B. So a constant may move through the dot product as well. If we take a vector and we take the dot product with itself, that is actually something interesting, because then we get, well, let's take A dot A for, let's say, this vector. That is equal to ax squared plus ay squared plus az squared, which is the length of A squared. So a length is always positive. So the dot product of a vector with itself is always larger or equal to 0. Well, when is it 0? That's the case for the null vector, the vector with only zeros. We also know that, so if A dot A equals 0, then A must be equal to the null vector. So these are some of the properties of the dot product. So we have defined one of the definitions for the dot product. We also see that for vectors in this form, let's say Cartesian form, we know how to write out the dot product as well. But I want to come back to this form again. And I'll need a bit of space, so I will remove this. the dot product is also useful to see if two vectors are perpendicular or not. So let's look at the form A dot B is equal to the length of A times the length of B times the cosine of theta, where theta is the angle between these two vectors. Let's see what happens if we look at different angles. So we could look at 0, 90 degrees, 180 degrees, 270 degrees, and 360 degrees. And of course the cosine function extends both to the right and to the left. I'll write here the radians, pi over 2 pi, 3 pi over 2 and 2 pi. And the cosine function looks like this. It is 1 to start off at 0, then it is 0 at 90 degrees, minus 1 at 180, 0 at 270 degrees, and of course this continues. But this spot is interesting. If the angle between two vectors is 90 degrees, so if A and B are perpendicular to each other, and this is the symbol for it being perpendicular, then we know that cosine of 90 degrees is equal to 0. So the dot product between these two vectors is also equal to 0. And the converse is also true. So if A times B is equal to 0, and of course A isn't equal to the 0 vector and B isn't equal to the 0 vector, because that would just be a silly case, then the two vectors are perpendicular to each other. So this is another property based on the original definition of the dot product. That is it for the dot product. So the definition, some properties, and some extra properties. These are all the videos for week 1, and I wish you good luck with the exercises.